Now are we good? Perfect. Assalamu alaikum, everyone. My name is Rawad Turko. I'm a second year medical student. And today, inshallah, we're going to be talking about nucleotide metabolism. So for those of you who've studied this lecture, you should know that it's, a fairly easy lecture. There's not much to understand, but there is quite a lot to memorize. There's quite a few clinical scenarios, and there are quite a few drugs. But inshallah, it should give you a taste of second year a little bit. And it's a very, very interesting lecture. It's personally one of my favorites. Sorry, it is my favorite from MOL 2 and probably all of MOL. And yeah, without further ado, let's just get into it. These are the objectives for today. We're going to be reviewing nucleic acids first. Okay, so similarly to how Dr. Hannah taught you this lecture. Then we're going to get into the overview of metabolism for both purines and pyrimidines. Then PRPP synthesis, which we will get to, inshallah. And then purines, de novo, and the salvage pathways. Then we're going to be talking about deoxyribonucleotides. Then degradation and gout. Then pyrimidine biosynthesis. So we were talking about purines previously. Then we're going to talk about pyrimidines. Then we're going to get into the pharmacology and a few clinical scenarios. And then we're going to do some questions. So the way I've organized this lecture, and I've sort of reorganized it a little bit from how Dr. Hannah taught you, is that we're going to go through everything, all the normal pathways first. Okay, so the way you were taught this lecture is that you would take a pathway and then you would learn an enzyme, for example, and then you would learn of a clinical scenario that has to do with that same enzyme's deficiency. And then you would move forward. The way I've reorganized this is we're going to be going through everything the way it happens normally. So normal pathways, every single enzyme is working the way it should. Then we're going to stop there. And then we're going to review everything we learned while taking clinical scenarios. Okay, so that way you should learn everything, the way it's working normally, physiologically in your body. And then after we're done all of that, we'll take some clinical scenarios. Does that make sense? So if you guys see an enzyme or something, and if you've studied this lecture and you see me teach you about an enzyme, and then I don't give you that enzyme's deficiency or a clinical scenario related to that enzyme, then it's probably because I'm going to give it to you later on in the lecture. Okay, so don't freak out too much. And finally, if you guys have any questions at all, please don't. Yeah, I'm not going to be able to go back to the chat too often. If you have a question, please, you can just feel free to unmute and interrupt me in the middle of my teaching. I don't mind at all. Just make sure that you guys, by the end of this lecture, fully understand it. For those of you that are watching this on YouTube, like watching the recording, inshallah, this should be enough to get you through both lectures of nucleotide metabolism parts 1 and 2. But I do suggest, as for all other lectures, that you do at least hit the slides once, just so you could look at all the pictures that Dr. Henna's used in case she wants to reuse any of them, and in case she mentions something fairly low yield that I forgot to mention in these slides. But this should be enough, inshallah. Let's get into it. So, review of nucleic acids. You guys should know from MOL 1 and, just from all of medical school, that we have these things called nucleotides. All right. So nucleotides are made up of basically three things. The first things are nitrogenous bases. These are your purines or your pyrimidines. Can somebody unmute quickly and tell me two examples of purines?
Purines, adenosine, and guanosine.
Guanosine, right. Okay, well, actually, these are so. See, I'm glad you made that. It's a very, very minor mistake, but I'm glad you made that minor mistake. It's actually adenine and guanine. When we use the suffix "sine," so adenosine and guanosine, we're actually talking about the nucleoside. We'll get into that. We'll get into that in a little bit. But when we say nitrogenous base, as in it's just the base, then it's adenine and guanine. Okay, so those are your purines. You guys remember the mnemonic? It's pure as gold, purine, adenine, guanine, pure as gold. So this is what this is what a purine would look like. If you guys remember, purine has the double ring. The way I remember it is that it's like sort of opposite. So it's a shorter word, but it's a double ring. And then the longer word is a single ring. It's sort of a weird way to remember it, I know, but so purine's shorter word, it's a double ring. So this is a purine, all right? It's adenine or guanine, again. And then you have your pyrimidines, which are thymine or cytosine, or cytosine, I guess would be cytosine, right? Okay, now let's get into nucleosides. So nucleosides are the same nitrogenous base that we took here. So it's the same nitrogenous base, but this time we add a ribose sugar. So this is your nucleoside. This is what we would call adenosine, right? Or guanosine. So for purines, the nucleoside for purines ends in SINE, sine. So adenosine or guanosine. All right. But for pyrimidines, it ends in dene. So cytidine or thymidine. Right? Dene. Sorry, not I don't know if I said sine, but dene for pyrimidines, seen for purines. Again, this is just a review. You guys should know this. For this lecture, don't spend too much time on this concept. This is just to sort of, help you set that concept in your mind, set it in stone, basically. All right, so this is your nucleoside. Okay, it's just the sugar, the pentose sugar, plus that nitrogenous base, whether it's a purine or a pyrimidine. Now we get into the actual nucleotide, okay, which is the nucleoside, which is the nitrogenous base plus the sugar, this time with a phosphate group or multiple phosphate groups. So it's whether it's one or two or three. Okay, so we have the nucleoside, and then you add a phosphate group. Okay, and then it becomes that nucleoside. So you take that nucleoside name, for example. So it's adenosine, and this time you add the second word, which is however many phosphate groups you have. So if it's one phosphate group, then it would be called adenosine monophosphate. If it's three, then it's adenosine triphosphate. Okay, and same thing, if it's a pyrimidine, then you would say, for example, thymidine monophosphate, thymidine triphosphate. Does that make sense? So you take the nucleoside side, and then you add the number of phosphate groups. Okay, does that make sense so far? So what would this be, for example? This picture that I don't know, I can't really point, but this picture that I'm showing you right here, this picture, what would it be? It's a purine, and it has one phosphate group, not three. So it would be, for example, adenosine monophosphates or guanosine monophosphates. Does that make sense? Because it's a purine ring, and it's one phosphate group. Does that make sense?
Yes.
Okay, perfect. So these things are, they're very easy to memorize because you guys take them so very often. But sometimes you might forget that you should actually sit down and try to understand what these words mean. Nucleoside, nucleotide, like when we say adenosine triphosphate, ATP, what exactly are we saying? What does that structure look like? You're not going to get any questions on this. They're not going to give you a structure and tell you what is this called, but it will make things a lot easier for you if you need to memorize any enzyme names. For example, if you need to memorize an enzyme name, it's important to know, or it's helpful to know what that structure sort of looks like. So because you could get the function of that enzyme just from its name, just by knowing what exactly we're talking about. What does the structures look like? What does the precursor and the results look like? What does the product look like? Okay. Okay, now let's get into the metabolism overview. Okay, so again, we said we have a nucleotide. Okay, that's made up of a pentose sugar, a nitrogenous base, and the phosphate group. Now, let's group them together, the pentose sugar with the phosphate groups. Okay, so let's group those two together. Those two things are going to come from one source when we're making our nucleotides. That source is called PRPP, or phosphoribosyl pyrophosphates. Okay, we're going to get into that very, very soon, but just know that we're getting our pentose sugar and our phosphate groups from one, or sorry, the phosphate group, the one phosphate group, we're getting it from one source, okay? And then we're getting the nitrogenous base from a different source. That source can be whether, or if we're talking about purines, it can be made, that nitrogenous base can be made either de novo, which means from the beginning, or from like a newly, which means you're basically building it from scratch. Or you could salvage that nitrogenous base from elsewhere. You could take that same base and just clip it on to a PRPP molecule, and there you have it. You have a nucleotide. Okay, does that make sense so far? So I have a nucleotide. It has three different components: the pentose sugar, the nitrogenous base, and the phosphate group. The pentose sugar and the phosphate group are coming from one source. The nitrogenous base is coming from another source. If it's a purine, it can be made either from scratch, which we call de novo synthesis, which in Latin literally means from the beginning, de novo synthesis, or it can be salvaged from the salvage pathway from different, like regular cell turnover. Like, for example, when cells die and they give up their DNA, or they give up their nitrogenous bases, instead of making those nitrogenous bases from scratch, sometimes we just take the ones that we already have, those readily made ones, and we just clip them onto a PRPP molecule, and there you have it. That's a nucleotide. Okay. So in purine synthesis, the first nucleotide to be made is inosine monophosphate, IMP. Let's see, that's kind of new. That's new than from what you've taken so far. We've taken adenosine, right? Adenosine monophosphate, triphosphate, whatever, and guanosine. Now we're going to be taking this thing, which is called inosine monophosphate. All you have to know is that this thing, IMP or inosine monophosphate, is the first nucleotide that's made in purine synthesis. It's the first thing that's made. So, for example, if we have synthesis of purines, we want to make, for example, an AMP molecule, adenosine monophosphate molecule. You can't just go ahead and make AMP, best take, right? You know what I mean? You have to make IMP first. And then from IMP, you can convert it to either AMP or GMP. So either adenosine monophosphate or guanosine monophosphate, right? This is, again, purine synthesis. So inosine monophosphate is the first nucleotide that is made in purine synthesis, okay? And again, this is a nucleotide, okay? So again, the nucleotide, because it's made up of three structures, it has the nucleoside, right, which is the pentose sugar, plus just the nitrogen base, and then it has just the nitrogen base. Like if we go back here, you guys remember we were talking about nucleoside, nitrogenous bases, and nucleotide. Okay, so for IMP, the nucleotide is called IMP, inosine monophosphate. Okay, now I want somebody to answer this question. Okay, this is just basically it's just a semantics question. Okay, it's just talking about the meaning of certain words. So if the nucleotide is called inosine monophosphate, what would the nucleoside be called? Can anybody tell me?
Wait, can you repeat?
Sure. So we have this nucleotide that's called inosine monophosphate, IMP. Okay? Inosine monophosphate is the nucleotide, as in it's the nucleoside plus the one phosphate group. That's what the monophosphate is there for.
So
If
it's inosine.
Exactly, I'm so glad. Yeah. So the nucleoside is just called inosine. It's that simple. Okay, but then the nitrogenous base in the inosine, because again, inosine, when we say inosine, we're talking about the nucleoside. That's the pentose sugar plus the nitrogenous base. So what do we call this purine base, this nitrogenous base in inosine? We call it hypoxanthine. This is where this one concept caused quite a bit of confusion in my batch last year, because usually the nitrogenous base is called adenine, so then its nucleoside is called adenosine, right? It's fairly simple. But in this case, we have the nitrogenous base or the purine base called hypoxanthine, and then its nucleoside called inosine, and then the nucleotide called inosine monophosphate. Okay, so just remember, when we say inosine, we're talking about the nucleoside. When we say hypoxanthine, we're talking about the purine base that's in inosine. Does that make sense? I really hope it does.
Yeah, it's clear.
Okay. Okay, perfect. And again, last thing I want to get into, this is again a very, very, like it's an overview. Okay, so don't feel too bad if it's not starting to make sense so far. It's gonna make sense by the end, inshallah. And again, last thing is the degradation of nucleotides yields xanthine. So we said that there's hypoxanthine, right? So if you degrade that a little bit, you get xanthine. If you degrade xanthine a little bit, you get something called uric acid. Uric acid is very, very clinically important in this lecture. Okay, you'll probably get most of your questions from this lecture will be something to do with uric acid or hyperuricemia. Sorry. All right. Now let's get into it. Now, you guys remember I talked about something called PRPP or phosphorybasyl pyrophosphate. That's where I said we get our pentose sugar plus the phosphate group from. All right. Now this PRPP, of course, we need to get it somehow, right? If we need to make a nucleotide, we need a way to get this PRPP in our body. We need to have it ready so that we could attach our nucleotide on it. All right, or we could build up our nitrogenous, or not nucleotide, our nitrogenous base. So we could build up this nitrogenous base onto this PRPP to make a nucleotide. We need to have this PRPP in our body somehow. Where do we get this phosphoribosyl pyrophosphate? We get it through the HMP shunt, the hexose monophosphate shunt. If you guys recall from your glycolysis lecture in MOL 1, you took something called the HMP shunt. Now, I don't want to get into that at all. It's not important whatsoever to know in this lecture, not at all. All you need to know is that this HMP shunt is an alternative pathway to glycolysis that produces two things: NADPH, which that's probably the important one. But for our case, the thing that we really care about is the other product, the ribose 5-phosphate. All right? It produces this HMP shunt, the ribose 5-phosphate, and that's where we get our phosphoribosylpyrophosphate. Pyrophosphate. Now, let's just take a second. Let's just take a breath and let's look at the structure a little bit. Because again, I mentioned it's not important at all to know the structure. Not at all. Okay. If they bring you a picture like the one that you see here on your screen, you won't be required to know what it is. But it does make things so much easier. Okay. So let's look at this first thing. Let's look at the ribose 5-phosphate. What do you see? We see a pentose sugar. All right. That much makes sense. A pentose sugar. And then we see a phosphate group. If you guys see the P there, a phosphate group attached to the 5' carbon of this pentose sugar. Makes sense. That's why we call it ribose 5-phosphate. It's a ribose with a phosphate group on the 5'. Ribose 5-phosphates. Okay? Now, we need a way to take this ribose 5-phosphate and attach a pyrophosphate group on the 1' carbon. A pyrophosphate, again, you don't need to know what a pyrophosphate is. All you need to know is that it's a thing that we put on this ribose 5-phosphate to come up with PRPP. Okay, so what would the enzyme be? PRPP synthetase. Fairly easy. You want to make PRPP. What's the enzyme called? PRPP synthetase. All right, this is the first step in both the de novo and the salvage pathways of purine synthesis. Okay, now, just as a kind of refresher, we have nucleotides. We want to get our nucleotides from somewhere, right? But they're made up of three things. They're made up of the pentose sugar, they're made up of a phosphate group, and they're made up of a nitrogenous base. The nitrogenous base, we said we can make it from scratch, from the de novo synthesis pathway, or we could just salvage it and reuse it from elsewhere in the salvage pathway. But either way, no matter where we get our purines from, we need a way to attach, we need a pentose sugar and a phosphate group. Where do you get this from? The PRPP. That is why PRPP, and specifically this reaction, this synthesis of PRPP, so the enzyme PRPP synthetase, this is the first reaction. This is important in both the de novo synthesis and the salvage pathways. Because either way, regardless of how we get our purines, we still need something to attach them on or attach it on, right? Our nitrogenous base or purines or pyrimidines or whatever. We need something to attach it on, and that's where you're going to get it from. You're going to get it from your PRPP, your 5-phosphoribosyl 1-pyrophosphate, or you just have to know PRPP. It's not that important. But again, knowing the name will probably help you in solving a few questions or knowing at least the enzymes. Okay, now, we said we have this reaction, PRPP, and we said that this is the first step in making purine nucleotides, right? Nucleotide, like eventually you're going to make AMP and GMP and IMP, I guess. Those are your purine nucleotides, adenosine monophosphate, guanosine monophosphate. So if we have too much of those in our body, if we have too much AMP or GMP in our body, we need a way to stop this reaction from happening because we don't want to make more. This is a type of feedback inhibition. So what do we say is true about this enzyme PRPP synthetase? It is inhibited by purine nucleotides. This is a type of feedback inhibition. Okay, so it's the first step of nucleotide metabolism or nucleotide synthesis. And the end product, which is AMP or GMP, they go back, and if levels of them, if levels of these purine nucleotides get too high in the body, these molecules, these nucleotides can actually go back and inhibit this first step, the PRPP synthetase step. Okay? And PI activates this step. This is an inorganic phosphate. PI, by the way, it's an inorganic phosphate because as you see here, this step utilizes ATP. Okay? So inorganic phosphates activate this enzyme. But the end product, which are purine nucleotides, inhibit this enzyme. That second point about the purine nucleotide, about the feedback inhibition, I really want you to remember that very, very well. It's going to be very important later on when we start getting into the clinical scenarios. Does that make sense so far? If it doesn't, please let me know. We can go over this again because this is a concept that you need to have, memorized like the back of your hand in order to understand the rest of this lecture. Do we understand this?
Yeah, it's clear.
Okay, perfect. All right, now let's get into purines de novo synthesis. So again, we mentioned de novo synthesis. What did we say that was? That is when you build up your purines from the beginning, from scratch. So again, de novo, it means anew or from the beginning. That is literally what the word means in Latin, or what the phrase means, de novo. Okay, from the beginning. So we're taking our PRPP, we're taking this molecule, this phosphoribosol pyrophosphate, and we're building up. We're going to keep adding atoms onto this molecule, keep throwing on atoms until we have a purine ring, or purine double ring, I guess. And then we would have a nucleotide. So what are the atoms? So we said we're going to throw atoms onto these things. Where do we get those atoms from? We have glycine, aspartate, glutamine, carbon dioxide, and tetrahydrofolates. Okay, I highlighted glycine, aspartate, and glutamine because it's very important that you remember these three amino acids, because there might be a question about them. And actually, in fact, there was, I think last year, if I remember correctly, there was a question about these three things. And just remember the mnemonic gag that Dr. Hannah used in her slide. It's more than enough. So if she ever asks you which amino acids are required for purine synthesis, then you would know it's glutamine, glycine, and aspartate. GAG, GAG. All right, and then carbon dioxide, not that important to know. Tetrahydrofolate is also very important to know. Okay, but again, that's going to be fairly obvious once we start getting into the pharmacology of things. Okay, you're going to see that there are a lot of drugs that act on and sort of affect the way that our body uses tetrahydrofolates. Again, we'll get into that. And again, the final product of this whole thing, of the de novo synthesis, is IMP, ionizine monophosphate, which is later converted to either AMP or GMP. Okay? So I know this picture might look like a bit much, but the very good news is that we only need to know this first reaction. What better could you want, right? From PRPP to the phosphoribosylamine thing, that's the only reaction you actually need to know from the de novo synthesis. You do need to know a few other things, but in terms of like which reaction is this, which number, like which enzyme, this is the only one you need to know. So, and that would be the second step. Because again, what did we say the first step was? PRPP synthetase. Okay, taking that five. The first step was PRPP synthetase. That's taking the ribose 5-phosphate from where? The HMP shunt. Again, an alternative pathway to glycolysis. So you take this ribose 5-phosphate and you attach a pyrophosphate group on the 1' carbon. Not that important to know, but again, you'd have this PRPP. Now you need to change this PRPP into something called phosphoribosylamine. Now again, and I will always stress on this, it's not important to know the structure, but it makes things 1,000 times easier. Okay, because look at this enzyme name, amidophosphoribosyltransferase transferase. It's too long. But if you just know what we're trying to do here, what we're trying to do to this PRPP molecule, immediately you'll know the enzyme without even trying to memorize it. Okay. The point of it is that you want to take this pyrophosphate group that we put on the 1' carbon, and you want to switch that out within a amine group, or amine group, whatever you want to call it. Do you guys remember that amine group thing? Amine group, right? So what do we call that enzyme? Amidophosphor, or actually this name is slightly different than the one that Dr. Hannah used. The enzyme name is phosphoribosol pyrophosphate amidotransferase. Okay, because you're transferring the pyrophosphate to an amine group. Okay, so it's called an amidotransferase. This second step requires glutamine. Okay, so we said here that using the de novo synthesis, we need 3 amino acids. One of them is glutamine. That's where we need it in the second step. All right, so we need glutamine for this enzyme, phosphoribosol pyrophosphate amidotransferase. Again, you just need to know the word amidotransferase. You don't need to know the beginning part. Just know amidotransferase. That's good enough for this reaction. What's important is that this is the committed and the regulated step. All right, so you guys know this whole thing about committed steps. Committed steps is a step that basically once you take the step, once your body converts this thing into this thing, that means there's only one product that you can get out of this reaction. There's only one way this pathway can go. Okay, but there are many other pathways that, as you guys know, there are many other pathways that cross over and they overlap, and this enzyme can be or this product can be a substrate for something else, and it can actually go in this pathway and that pathway. No, but in this case, this step, the amidophosphorase or the amidotransferase step, this is our committed step. So once we take the step, there's no going back. That's basically what that means, and it's a regulated step. Okay, so I mentioned that we have purine nucleosides that go back and inhibit this step. Do you guys remember that? I said that the end products, which are AMP and GMP, purine nucleotides, they can go back and they can inhibit the step at the first stage, which is PRPP synthetase, but they can actually go back and inhibit this entire process also through this step, which is the amidotransferase step. Okay, so it's inhibited by the end product, it's mentioned, and it's activated by PRPP. That makes sense, right? If you have more of the substrates, you're going to have more of the product. You're going to be pushing that pathway down in this direction or towards the end product. Okay, so again, just to sort of recap everything, because now is when we're going to start rolling a little bit. We have our PRPP, which we get through the enzyme PRPP synthetase, which basically this whole reaction is converting ribose 5-phosphate from the HMP shunt to PRPP, or phosphoribosol pyrophosphate. Then our second step in de novo synthesis is taking this PRPP and basically switching out a pyrophosphate group with an amine group. And this is through the enzyme amidotransferase to make phosphoribosylamine. All right. And again, this is where we also need glutamine here. So we needed, so again, we need glutamine in this second step. And we're making phosphoribosylamine. All right. Now, the good news is that's as much as you need to know in terms of like actual reactions. So as you guys see here, we talked about the first step and the second step, but steps 3 to 11, you don't need to know them. All you need to know is that you need tetrahydrofolate in 2 different steps. In one of those, 3 to 11, you need tetrahydrofolate. Or again, where do you get tetrahydrofolate from? Folic acid. And the end result is inosine monophosphate, IMP. And from IMP is where you get AMP or GMP. Okay? All right. Now, we've reached the end of de novo synthesis. Now we have IMP somehow. We have IMP. Now, as I mentioned, we need to change it into either AMP or GMP. Okay? Now, here's the fun part. There's this thing about mycophenolic acid. You can choose to ignore that for now because we will come back to it later, as I mentioned. As I mentioned, we're going to get into the pharmacology of things later on. All right, so right now you don't really need to focus too much on this drug, but I do want to bring your attention to one thing. If you look here, if you look at the diagram, you'll see that we have IMP right there in the middle, and then it can go. There's 2 arrows, coming out from IMP, heading in 2 opposite directions. One of them is giving you GMP, like that pathway is giving you GMP, and the other one's giving you AMP. But if you notice, if you look at the red boxes, the pathway that yields GMP requires ATP, and the pathway that yields AMP requires GTP. Why do you guys think that is? Can anybody tell me why? Why do you think, like, for example, okay, so AMP, we know that AMP, adenosine monophosphate, eventually becomes ATP, adenosine triphosphate. Okay? Why do you think ATP can go back and basically is needed to make the other purine nucleotide, GMP? Does that make sense? Am I making sense to you guys? Can anybody tell me why we have this phenomenon? Okay, that's fine. That's fine. That's okay. It's a bit of a. I'm not sure if maybe I worded it slightly the wrong way, but this is a concept that's important because it shows you, like, subhanallah, how much our body is constantly working towards homeostasis and how much it's working towards a balanced state. So let's say you have too much GMP in your body, way too much GMP. And by the way, I'm talking about just GMP. I'm not talking about AMP, okay? Because we know that both of these things can go back and inhibit the first 2 steps of purine nucleotides or de novo synthesis, right? Either at the PRPP synthetase step or at the amidotransferase step. But I'm talking in this case about just GMP. For example, GMP is too high. What's it going to do? eventually is going to be converted into GTP. Now, the body's telling itself basically, we have too much GMP. We need to make some AMP. We have too much GMP. We need to make some AMP. So what are we going to do? We're going to take this GMP, we're going to turn it into GTP, and then we're going to use that GTP to make more AMP. Does that make sense? So that's why you see here the red box on the left side, right next to aspartic acid. I'm not sure if you guys can see. I'm sure you can't see where I'm pointing, but I think you guys know what I'm talking about. The GTP right there in the red box. That's why we use that. We use GTP to make AMP, and then we use ATP to make GMP. Okay, so this is a way in which if your body has too much GMP, then it can use that to make more AMP to sort of reach a more balanced state. And that's the same reason why, in the same way that we have feedback inhibition, that's the same reason why GMP can then go back and inhibit IMP dehydrogenase, which is the first step, the first enzyme to make GMP. I feel like I've lost you guys. Can somebody confirm or deny that?
You kind of lost me, but then not. I got the
Okay.
road of it.
Okay, I'm gonna just repeat this concept just because I want all of you to get it. And if you guys do understand this point, just leave a thumbs up if you don't want to open your or like raise your hand. Thumbs up or like give me any reaction. And Mariam, if you could please just let me know once everyone has their hands raised. Okay, I'm glad. I see a hand raised. All right, so I'm gonna explain again. We have IMP. We have IMP. Now we want to make AMP or GMP. Okay, because again, this whole thing, everything we're talking about so far, is to make purine nucleotides. That's your adenosine monophosphate and guanosine monophosphate. But the first nucleotide that we make in de novo synthesis is IMP. So now we need to change it into either AMP or GMP. Now, the body has a certain way of working where if it has too much of one thing, it's going to stop making that thing, first of all, and then it's going to go and make something else to accommodate, to sort of balance things out. So in this example, if we have too much GMP in the body and not enough AMP, GMP is going to go back and inhibit its own production. That's called feedback inhibition, again, by inhibiting this enzyme, which is IMP dehydrogenase. So you guys see it? That's the first enzyme that we need to make this final product, which is GMP. So IMP dehydrogenase is inhibited by its end product, which is GMP. Okay, and in the same way, AMP, which is the end product of the other pathway, goes back and it inhibits adenylosuccinate synthetase. Okay, which is the first enzyme that we need to make AMP. So that so far, this is an example. Both of these things are examples of feedback inhibition. Okay, so that's the product, the end product, GMP or AMP, going back and inhibiting its own synthesis in order to not make too much. Okay, another thing that the body does to basically balance things out or to accommodate is it uses one product as a sort of as a substrate for another product. So we have GMP. If you guys look at where I'm pointing, this is the best way that I can illustrate exactly what I'm talking about because I can't use the pointer on Canva. So if you guys look at GMP, for example, if you pretend that the diagram is in front of me, if you look at GMP is going to be turned into eventually GTP, right? GTP is used as an energy source to make eventually AMP. Okay, this is a way in which our body accommodates so that if we have too much GMP, we inhibit the production. First of all, we inhibit the production of more GMP, and then we go and we activate the AMP process. Does that make sense?
Yes.
Okay, perfect. Okay. Again, this is I'm trying to make sure to hit as many possible difficult concepts as possible so that by the end of this lecture, by the end of this PAL, inshallah, you guys should have no problems whatsoever in this lecture. Again, IMP dehydrogenase is inhibited by mycophenolic acid. We're going to get back to this later, okay? You don't need to spend too much time on it now. Okay, let's move on. This is the de novo synthesis. Now we're done. We're done the de novo synthesis. We have our final products, which are AMP and GMP. We're done the de novo synthesis, okay? But again, you guys have noticed these are 11 different steps. You guys look at this picture right here, 11 different steps. It's too much. It's too much. We need glycine, we need aspartate, we need glutamine, and we need carbon dioxide, tetrahydrofolate, and ATP. It takes a lot of energy out of the body to just make a nucleotide, a purine nucleotide from scratch. So our body's lazy. It has ways to sort of reuse its shortage, or sorry, reuse its supply of nucleotides without breaking everything down and then building it once up again, back up again. So we have this other pathway called the salvage pathway. And the name, it's pretty self-explanatory. What we do is that we take already made nucleotides and we attach them onto a PRPP molecule. Okay, so there's nothing to be done. Everything's already set. We don't need to make anything. We don't need to switch out an amine group for a pyrophosphate group. We don't need to add any, you know what I mean? All we need to do is just take this thing that's already done and just clip it onto a PRPP molecule. Fairly simple, right? And the enzyme, this is why I mentioned previously that it sort of helps you to understand what the enzyme is like, what the name of the enzyme means, because it will help you a lot in like never forgetting it. Like, and because when I did this lecture last year, because I had time to spare, to be honest with you, and because when I did this lecture, I found it so interesting. I sat down and I genuinely wanted to understand why the enzyme was named that way. And subhanAllah, until now, I haven't forgotten the name of this enzyme or any of the other enzymes, just because I spent time on trying to understand what this enzyme was trying to do exactly. Okay, so again, the salvage pathway, reuse of preformed bases from cell turnover or diets. Okay, so you can get these purines bases also from your diet. Okay, you can get them from mostly it's seafood and some red meats, stuff like that. So if you guys see a question about like somebody who eats a lot of seafood, just know they're ingesting a lot of purine bases. Okay. So again, these are the three purine bases that we've talked about so far. We've talked about adenine, guanine, and hypoxanthine. Okay. Quick little recall question from like 10 minutes ago. What's the nucleotide called for hypoxanthine? Hypoxanthine, the nucleotide for hypoxanthine. So hypoxanthine would be the purine base. It's just a nitrogenous base. What do we call this base when it's attached to a pentyl sugar and one phosphate group? It's a full nucleotide. Do you guys remember? It's right there. Actually, like if you just look at the diagram, it's right there. Follow the line. Hypoxanthine turns into what?
It turns into IMP.
IMP, inosine monophosphate. Okay, that's a concept that you guys need to memorize pretty well. Okay, so hypoxanthine is the purine base. IMP is the actual nucleotide. So inosine monophosphate is the actual nucleotide, and that's again the final product of de novo synthesis of the purine biosynthesis. It's kind of a tongue twister, but you guys get it. Okay, so fairly simple. We have these three purine bases. Just take them and just put them onto a PRPP molecule. Okay, just put them on, clip them on, and then you're good. So what is this process called? Phosphoribosylation. Okay, ribose as in the ribose sugar, phospho as in the phosphate group. So basically, this word phosphoribosylation, all it's telling you that we're taking this base and we're putting it onto a ribose sugar with a phosphate group. Phosphoribosylation. Okay, and then you put a word first. You put a word before phosphoribosylation to describe which purine base we're talking about. So in the case of adenine, what do we call this enzyme that takes adenine and turns it into AMP? We call it adenine phosphoribosylribosyl transferase. Okay, because it's transferring this adenine into a PRPP, or we're phosphoribosylating it. Does that make sense? So it's called adenine phosphoribosyl transferase. Okay, now this enzyme, this first one, the one about adenine, so it's called APRT, or adenine phosphoribosyl transferase. You don't really need to remember it. Okay, it's not very clinically important. You likely will not get any questions about it at all. What you do need to know is the second enzyme, which is HGPRT. It has a very, very, very high yield clinical scenario, or very high yield syndrome, very high yield disorder behind this enzyme. We're going to get into it later. But again, in the same way that we did adenine, now we have one enzyme. It's just the one enzyme that acts on both hypoxanthine and guanine. Okay, so it's one specific enzyme for adenine, and then it's one specific enzyme for both hypoxanthine and guanine. What do we call this enzyme? It's pretty simple, right? Hypoxanthine, guanine, phosphoribosyltransferase, HGPRT. Okay, and it turns hypoxanthine to IMP and guanine to GMP using this PRPP molecule. Does that make sense?
Yes.
Okay, perfect. So HGPRT for hypoxanthine and guanine, APRT for adenine, but again, you don't really need to know it that much. Okay. All right. I'm sort of torn on whether to sort of recap everything again because we're done purine synthesis. Like this is basically all. Oh, actually, we have one step left, but it's like in terms of purine bases, we're done that, or purine nucleotides, we're done that. So I'm sort of torn on. You know what? How about this? Let's keep going for now. Once we get into the clinical scenarios, we'll recap everything again, and then we'll take some of the clinical stuff. Yeah.
Rawad, someone said to recap now.
Okay. Sure. No worries. Let's recap really, really quickly. Okay. I don't want to take away too much of your time. I'm gonna skip the review of nucleic acids just because I think that that's something that you could probably do on your own very quickly. Let's start here. So we have a nucleotide. Okay, a nucleotide is very simple. It's made up of a nitrogenous base. It's made up of a pentose sugar, and it's made up of one or more phosphate groups. Okay, now to make this nucleotide, it has three components, as I mentioned. We need different things happening at the same time. Okay, because since there's three components, you're not going to get all three components from the same source. That doesn't make any sense. So what we're going to do is we're going to take this ribose and the phosphate together. So this white thing and this black thing, this pentagon looking thing and the circle. Those two are coming from the same source, which is PRPP. Okay, PRPP again is basically it's something that you get from how about this? Well, let's just go through the actual order of things first. So again, you have this pentose sugar and you have this phosphate group. They're coming from one source. Then you have this nitrogenous base. That's the thing in red that you guys see, those two rings. That's coming from a different source. So that exact thing, those purine bases, you can either make them from scratch, or you could take them from other cells and just clip them on to that PRPP molecule we talked about. Okay, the first thing, which is making them from scratch, that's called your de novo synthesis, because the word de novo literally means anew or from the beginning. Or you could take it and you could salvage it from elsewhere and just clip it onto the PRP. That's called your salvage pathway. Okay. Now let's get into the actual let's get into PRPP synthesis first. So we talked about PRPP, right? That's your phosphoribosyl pyrophosphate. You don't really need to know the full name. Just if you know PRPP, that's enough. And this PRPP, and you need to get it from somewhere, right? It doesn't just spawn in your body. You have to get it from somewhere. Where do you get it from? You get it from something called the HMP shunt. That's something that you guys should remember from MOL 1. Okay? You guys, I'm sorry, I didn't check. You guys did take the HMP shunt, right? That whole thing with glucose 6-phosphate and
yes, yeah, okay, we did.
Okay, yeah. So this is something coming from the HMP shunt. Okay, so the HMP shunt, just to recap very, very briefly, it's an alternative pathway to glycolysis, and one of the things it produces is ribose 5-phosphate. From this ribose 5-phosphate, that's where you can make your PRPP molecule from. Okay, that enzyme is called PRPP synthetase, and it uses ATP as an energy source. All right, so we get our PRPP from ribose 5-phosphate from the HMP shunt, and it's the first step in both the de novo synthesis pathway and the salvage pathway, because either way we're going to need this PRPP molecule. It's very, very important to us, so we need to get it from somewhere. That's why this step, PRPP synthetase, is very important, and it's the first step for both the de novo synthesis pathway and the salvage pathway. Okay, moving on, then we have, okay, this is not, it's fine. And then we have our second step, then when we talk about purine, we talk about de novo synthesis as a whole. Okay, this is where we build our nitrogenous base basically from the ground up, from scratch. Okay, why isn't this? loading. It's fine. That's where we make our purine base from scratch, basically. And it uses 3 different amino acids that you guys need to know. Sorry, glycine, aspartate, and glutamine. GAG, G-A-G. We need these 3 molecules in order to make purine bases, in order to make purine nucleotides using the de novo synthesis, the de novo pathway. All right. So GAG, GAG, glycine, aspartate, glutamine. You guys we need these 3 amino acids in order to make any purine bases in the de novo pathway. And you guys should remember them because they might be high yield. And the final product of this entire pathway, the de novo synthesis pathway, the final product is a nucleotide. It's a purine nucleotide specifically called inosine monophosphate. It's called IMP. And from this molecule, from this IMP molecule, then you can make either AMP or GMP. And then you have it. Like there you have it. That's your entire de novo synthesis. Because the final aim, the final objective of this entire synthesis is to make AMP and GMP. That's what we want to do. Because these are your purine nucleotides. And then once you have AMP or GMP, you can add more phosphate groups on them. You can have ATP or GTP, right? Or you could change them back into, you know what I mean? You could do a bunch of stuff, but that's what we want to get to. We want to have AMP or GMP. How do we do that? First, we have to convert them. We have to convert IMP to either one of these things. So you take IMP, you convert it to either AMP or GMP. All right. So this is why isn't this kind of blurry? Can you guys still read this? Like the diagram? It's
yes.
A bit blurry.
Yeah.
Okay.
Yeah.
All right. So again, the second step in de novo synthesis, we talked about the first step. The first step being PRPP synthetase. The second step now is something we call amidotransferase. Okay, amidotransferase is the second step of de novo synthesis. That's where we take PRPP, which we got from ribose 5-phosphate. You guys remember that? We take this PRPP and we just add an amine group, where we basically switch out a pyrophosphate group with an amine group. The enzyme is called amidotransferase, and this is the committed and regulated step of de novo synthesis. Do not forget these words about this reaction, okay? Amidotransferase step is the committed and regulated step of de novo synthesis of purine nucleotides. And this step requires glutamine. Okay, so we mentioned here that we need glutamine, right? Glutamine and aspartate and glycine. This is where your glutamine comes in this specific reaction, amidotransferase. Okay? And again, it's inhibited by its end product. So this is a case of feedback inhibition. So the final products, AMP and GMP, then if we like this is a way for the body to maintain homeostasis. If we don't want to make too much of AMP or GMP, then these 2 molecules can go back and inhibit their own production by inhibiting this step, the amidotransferase step. Okay. Now, for the rest of the steps of de novo synthesis, all you need to know is that we need tetrahydrofolate a bunch. We just need it a lot. And it's very important for us. We need tetrahydrofolate. Just remember that because we're going to come back to it later. And the result, again, is inosine monophosphate IMP. Now, we have IMP. We want to make either GMP or AMP. Okay, the first enzyme that we need in order to make GMP is called IMP dehydrogenase. So you guys look at it, it's right here. It's where the arrows are pointing, the white arrow. You guys see that? That's where it's pointing, IMP dehydrogenase. That is inhibited by its end product, which is GMP. So this is another case of feedback inhibition. And same thing with AMP and with adenylosuccinate synthetase, okay? By the way, just as an extra little thing, you don't really need to remember adenylosuccinate synthetase. You do need to remember IMP dehydrogenase because as you guys clearly see, there is a drug that has to do with this enzyme. Okay, but adenylosuccinate synthetase, it's not that important. Okay, so again, you have this IMP. Now, from this IMP, you make either GMP or AMP, and then that's your de novo synthesis. Okay, GMP requires ATP as an energy source. AMP pathway requires GTP. Okay, I've already explained this concept, so I don't think we need to go over it again. And then the purine salvage pathway. So we're done right now from the de novo synthesis. Now, purine salvage pathway, as I mentioned, we already have a purine base. We have it either from our diet or from regular cell turnover, which means cells die and they give up their they give up their bases, their nitrogenous bases, and then you take them and then you just clip them onto more to other PRPPs, and then you have a full nucleotide. You don't even need to go through all the hassle and all the effort to make one from scratch. You could just take that one and clip it onto to a PRPP molecule. The enzymes that we need here are there's two of them. One of them is for adenine, so it's called adenine phosphoribosyltransferase transferase. Okay, because you are literally taking this thing, this base, and you're putting it onto a ribose sugar with a phosphate group, so phosphoribosyltransferase transferase. And the other enzyme is for both hypoxanthine and guanine, and it's called HGPRT, hypoxanthine guanine phosphoribosyltransferase transferase. Okay, you just take this base and you attach it onto a PRPP group. If you guys see here, this base, this base is literally right here, right? It's the same thing. All you did is you just attached it to a PRPP, which is, I don't know why it's tripping like that. It's this thing, okay? The pentose sugar with a phosphate group. And that's all you're doing. It's very, very simple, okay? And again, you don't really need to remember the APRT enzyme, the adenine phosphoribosyltransferase transferase, but you do need to remember HGPRT. Okay. All right. So whoever asked, is that clear enough? Is that okay? I'm gonna take that as a yes. Okay. So here's a little bit of a little twist. What's DNA? What's DNA? Do you guys know DNA? Like, what does it stand for?
Deoxyribonucleic acid.
Exactly. Deoxy means you're literally deoxifying. You're literally taking away an oxygen atom. Okay. Everything we've made so far is ribonucleotides. Ribonucleotides. Because if you see here, on the pentose sugar, there's an O group. You guys see that? This O group? This O group tells you that it's a ribonucleotide. It's not a deoxyribonucleotide, because if it was a deoxyribonucleotide, you wouldn't have this O group because you're taking away that oxygen. So these are ribonucleotides, but we need deoxyribonucleotides to put them into DNA. So what do? Now we have all our purine nucleotides. We have them from both the salvage pathway and the de novo synthesis pathway. Okay, we have everything we need. All we need to do now, this is the final step, and after you're done this step, khalas, you have a ready deoxyribonucleotide, ready to put it into DNA, ready to do whatever you want with it. All you need to do is just take away this little oxygen molecule, or this little oxygen atom, and you're good. Which enzyme do we use for that? Fairly simple. Ribonucleotide reductase. It says it right here, right? Ribonucleotide reductase. So if you guys see here, we have our ribonucleotide. Again, this is what it looks like. This is the pentose sugar. This is the base right here, and this is a phosphate group. And if you guys see here, look at the 2' carbon. It has an oxygen and hydrox, or sorry, I forgot what this is called, but there's an oxygen there. That's the point. So ribonucleotide reductase would take this thing, would take this nucleotide, and it would just take away this oxygen, and then you have a deoxyribonucleotide, and then you could put it into DNA. Okay. So all we need is this enzyme ribonucleotide reductase. Okay. Do you guys remember that whole oxidation reduction thing from high school chemistry, redox reactions? You guys remember that? So this is just an example of reducing something. Okay. Does that make sense? Deoxyribonucleotides. All it takes is just this one enzyme, ribonucleotide reductase. Now, it's inhibited by deoxy-ATP, deoxyadenosine triphosphate, because this is, and again, another example of feedback inhibition, because when you're changing something, when you're making deoxyribonucleotides, what might they turn into? DATP. So again, it's another case of feedback inhibition where the end product comes back and inhibits this step. Okay, this is an important concept. DATP, the other ones, fine, I guess, it's not that serious. This one's important. There's a specific case and a specific clinical scenario that has to do with this concept as a whole, like DATP inhibiting this thing. So does this make sense? Deoxyribonucleotides.
Yes.
Okay. All right. Now, we're gonna get into degradation and gout. Okay. So I know we still have pyrimidine synthesis to do. Inshallah, it's a lot easier than purine synthesis. But when we talk about gouts, specifically gouts, gout has to do with purine nucleotides, not so much pyrimidine nucleotides. Okay, so now we're done purine synthesis. We're going to talk about gouts and degradation of purines as a whole, and then we're going to get into pyrimidines, and then we're going to get into clinical scenarios. Okay, so what did I say about IMP? What did I say the what's it called? The base was in IMP? Hypoxanthine, right? So when we're when we're degrading purine nucleotides as a whole, IMP is going to be basically converted into inosine, and then inosine is going to be converted into hypoxanthine, and hypoxanthine is going to be degraded a little more to give you xanthine, and then xanthine is going to be degraded a little more to give you uric acid. Okay, so this is how it goes. IMP here, so again, this is basically summarizes everything. So PRPP here, then the de novo synthesis to give you IMP. Now from IMP, you can make GMP and you can make AMP, but those eventually can come back and can turn back into inosine. Okay, now once they need degrading, once the body decides there's too many purines, I don't need this many purines, I'm going to get rid of them. It takes this IMP and it turns it eventually into hypoxanthine and xanthine, and then into uric acid. And then uric acid is excreted in the urine. Okay, but once there's too many, there's too much. But if there's way too much purine degradation, okay, either we're producing too much uric acid because we're producing too many ribonucleotides, or we're excreting little uric acid, then we have this thing called hyperuricemia. Hyperuricemia, do you guys know what the suffix emia means?
In the blood.
In the blood. So hyperuricemia means too much uric acid in the blood. This thing, hyperuricemia, that's what's going to give you gout. Okay, gout is basically gout is caused by hyperuricemia or too much uric acid in the blood, and gout is basically when this uric acid that's supposed to be excreted out of your body, when there's too much of it in the blood, is going to go to your joints, and it's going to basically attach to your joints, and it's going to cause gouty arthritis, and basically it's going to deposit these things called monosodium urate crystals. Okay, does that make sense? You have degradation. Degradation of purine nucleotide eventually, that's all purine nucleotides, IMP, AMP, and GMP. Eventually, that's going to give you hypoxanthine. And then hypoxanthine eventually then will give you uric acid. Uric acid is supposed to be excreted by the body in the urine. That's what it's supposed to do. But if there's too much degradation or too little excretion of uric acid, then you have buildup of uric acid in the blood. That's called hyperuricemia. That's going to result in gout. Gout is basically deposits of monosodium urate crystal. By the way, urate is literally uric acid. I'm sure you guys know this by now, but the suffix ate just means acid. Okay, so aspartate, for example, another name for it is aspartic acid, right? Glutamate, glutamic acid. So uric acid, urates. So monosodium urate crystals in the joints, that's going to cause your gouty arthritis. And the classic sign, and you guys might get this in questions, is a nodular mass in the big toe. So you might hear, for example, that somebody's been feeling very uncomfortable in shoes lately. You know, they put on their shoes and it fits tighter than it's supposed to. Well, that's an indication, it's a sign of maybe gout, because it affects the big toe. So obviously if there's a nodular mass there, you're going to feel like your shoes are a bit too tight. So that's something to look out for in questions. Okay, degradation and gout. Again, everything we've talked about so far, all of it has a few clinical scenarios sprinkled in like here and there. But I wanted you guys to fully understand the normal pathways first before getting into the clinical scenarios. So does this make sense to everyone so far?
Yes.
Okay. All right. And Mariam or Yasser, whoever one of you checks, if there's anything in the chat, please do let me know. I'm not able to read the chat. Okay.
No, there's nothing in chat.
Okay, perfect. Thank you. All right. Now we're going to get into pyrimidine synthesis. This is a lot easier. So unlike purine synthesis, as we mentioned in purine synthesis, specifically de novo synthesis, when we want to create these bases, we basically have the PRPP molecules, and I mentioned at the start, you just throw atoms onto this PRPP molecules, and eventually you'll have a nucleoside. Okay. Pyrimidines are a little different. Pyrimidines, you basically form the base on its own. You form the pyrimidine base, and then you attach it onto the PRPP, and then you attach it to the ribose sugar. Okay. So it's a little different. This time is different. You only need aspartate and glutamine, so you don't need glycine. You do need glycine for purines. You need all three, in fact, for purines, but in pyrimidines, you only need aspartate and glutamine. And there's only 6 steps instead of 11. But again, you don't need to know all 6. And you don't need to know all 11 for purines. So I guess that point doesn't matter. And the final product is UMP. So does anyone remember yes, that I want you to answer this question, honestly. Do you remember the final product of purine synthesis, de novo synthesis?
The purine would be IMP.
Exactly. And in this case, in pyrimidine synthesis, UMP, uridine 5 monophosphate, or monophosphate. You guys can forget the 5. Uridine monophosphate. Okay. Okay, let's get into it. All right. Step number 1, carbamoyl phosphates. Okay, this is you're taking a bunch of molecules, including glutamine, and you're basically turning them into this molecule called carbamoyl phosphates through CPS2, carbamoyl phosphate synthetase 2. Now, why is it important that I mentioned 2? And why is it so important that you remember when we're talking about pyrimidine synthesis, it's CPS2, not CPS1? Because CPS1, if you guys remember, did you guys take urea cycle yet?
Yes.
Okay. For those of you that study, yeah.
CPS1 would lead to the formation of urea. And CPS2
in the
would
urea
be
cycle. Yeah.
And TPS2 would be for the pyrimidine.
Exactly. That's why you need to remember. Okay, CPS1 is in the what's it called? Urea cycle. Okay, that's that whole enzyme that has to do with ornithine and the other carbonyl phosphate, like that thing. That enzyme is different than this one. When we're talking about pyrimidine synthesis, the enzyme is CPS2, not 1. Okay, that's important. Again, you need glutamine and ATP because it says so right here. That's why we know that. That's true. And again, same thing in purine synthesis. It's inhibited by its end product, so inhibited by UTP. Okay? All right, perfect. And it's activated by PRPP. But that makes sense, obviously, because if we have PRPP, we have too much of PRPP, we're going to want to make purines and pyrimidines. So you're going to activate both pathways. So you make as many nucleotides as you can. All right. Now, we can skip these, the rest of these, the aspartate, transcarbamylase, or whatever. And we're going to focus on these last 2. These last 2, OMPG carboxylase and orotate phosphoribosyltransferase transferase, you don't really need to know the names. All you need to know that these are 2 domains of one enzyme. So these 2 make up one enzyme called UMP synthase. And that makes sense because UMP is our final product. Okay, so these last 2 enzymes, they're not 2 enzymes. They're actually 2 different domains of one enzyme. Okay, called UMP synthase. Again, there is a clinical scenario attached to this concept. We can go over it very quickly for now, but we will come back to it later on. Deficiency of this enzyme results in orotic aciduria. Okay, treated with uridine administration. Do you guys remember? I asked you before what is anemia means when we say hyperuricemia. It means too much uric acid in the blood. What does urea mean? Like the suffix urea. So anemia is in the blood. Urea is in the sorry, I zoomed in too much. Is in the urine. Right? So orotic aciduria, this is when you have too much orotate or orotic acid in your urine. Okay? Do you guys remember the whole thing about polyuria? You need to pee too much, polyuria. Same thing. Okay, so orotic aciduria. Again, we're going to come back to this later, but so far, all you need to know is step 1, CPS2, okay, inhibited by its end product, which is UTP. Okay, and you need glutamine for this step. Okay, now this is important. We basically have UMP now. Okay, UMPs then it goes the same for both purines and pyrimidines. You have this ribonucleotide, which is UMP. You need to turn it into a deoxy ribonucleotide. So instead of UMP, it needs to become deoxy UMP or DUMP or dump, as I like to remember it. And it's the same enzyme. It's ribonucleotide reductase. It's the same one as here. If I can go back. Same one as here. So ribonucleotide reductase turns ribonucleotides to deoxyribonucleotides. That's for both purines and pyrimidines. So it turns AMP to DAMP, and then it turns UMP to DUMP. Okay, and then DUMP is converted into DTMP through thymidylate synthetase. This is again another important enzyme, thymidylate synthetase, because again, what does the T stand for in epyrimidine? Thymidine, right? Or thymine, but again, the nucleoside is thymidine. So what are we doing here? We're switching out this uridine in the DUMP uridine. We're switching it out with a thymine. So what are we doing? It's a thymidylate synthetase. And thymidylate, again, the 8 stands for acid. It means acid. So it's basically the name for this nucleotide, DTMP. Thymidylate synthetase. Does that make sense? Guys, if this makes sense so far, raise your hands. Okay, I'm sort of worried that I don't see any hands. Is that because you guys are zoned out or because you're not understanding fully? Just check. Okay. Oh, I see a few hands. Sorry about that, guys. I didn't see. Okay. Perfect. I'm gonna try to move on. If you do get confused at any point, just stop me. I'm fine with that. Um, Again, just to recap this last point very, very quickly, you have UMP, which is the final product of pyrimidine synthesis, uridine monophosphate. Uridine monophosphate first needs to be reduced through the enzyme ribonucleotide reductase. So you need to take away this oxygen atom, turn it into DUMP or dump. Again, dump is not the actual name. That's just the way I like to remember it. And then DUMP is converted into DTMP through thymidylate synthetase. And thymidylate is another name for DTMP because since I guess this is sort of like extra information, but since it's called like deoxyribonucleic acid, since it's like acid, you could just say it's thymidylate, and the 8 means like it's acid. You guys get what I mean? And it's thymidine. So DUMP to DTMP through the enzyme thymidylate synthetase. And very importantly, this enzyme needs tetrahydrofolates. Okay, it needs basically it needs like a methyl group from the tetrahydrofolates. Okay, so remember that tetrahydrofolate is important for thymidylate synthetase. All right, let's move on. Now we can finally get into some pharma stuff. Okay, so let's go back to the very beginning, just really, really quickly. Okay, you have de novo synthesis, salvage pathway. Let's start with de novo synthesis. You have PRPP through the enzyme PRPP synthetase. PRPP to the phosphoribosylamine molecule using the amidotransferase enzyme. That's the second step of the de novo synthesis. This is the regulated and the committed step, and it's feedback inhibited, and it's activated. It requires glutamine. Okay, and then steps 3 to 11, so on and so forth. They need tetrahydrofolate, all that stuff. Now you have IMP. IMP, as we mentioned, can turn into AMP or GMP. GMP through the enzyme IMP dehydrogenase. Now, you have this thing called mycophenolic acid. This is a drug that basically acts on this enzyme, the IMP dehydrogenase enzyme, and basically, like try to think about it in a logical way. Any any what's it called? Any drug that would work on these enzymes. When I say these enzymes, I mean like any of these enzymes that have to do with like what's it called, nucleotide synthesis. Any of these enzymes would target rapidly dividing cells, right? Rapidly dividing cells, like for example, cancer cells or immune cells. So try to think about it in that way. So that's why a lot of these drugs that we're going to take, in the near future, that's why a lot of them are anti-cancer drugs, because they're targeting rapidly dividing cells. Because if you're rapidly dividing cells, what do you constantly need more of? If you're rapidly dividing, you constantly need more DNA, because you're going to be replicating your DNA over and over and over and over again, very, very rapidly. If you suddenly deprive that cell of very, very important components needed for DNA synthesis, what are you going to do? You're going to cause the death of these cells. So it's used to target cancer cells. It's used to also to target cancer cells and immune cells. In this case, mycophenolic acid is acting on IMP dehydrogenase, and it's used to prevent graft rejection. Okay, so if you do a skin graft or you do a organ transplant or something like that, you guys know that whole thing where your body can sort of reject that skin that's transplant, can sort of reject that graft, that skin graft, or it can reject organ transplants or stuff like that. We don't want that to happen. So what do? We give mycophenolic acid, and it basically deprives immune cells from these very, very important components that they need in order to divide rapidly. And thus you basically stop the immune response against a rejected graft. Does that make sense? So this is the first drug that we're going to take. It's called mycophenolic acid. Okay, and again, it's an inhibitor of IMP, or inosine monophosphate dehydrogenase. It deprives rapidly proliferating T and B cells, these are your immune cells, of key components of nucleic acids, and it's used to prevent graft rejection. Mycophenolic acid. Does that make sense? Okay. Let's move on. So I mentioned also, I'm sorry, I don't know why I didn't change the. Okay, I was supposed to change this diagram, but it's okay. We'll use another diagram for this slide. If you guys remember, we have tetrahydrofolate, and tetrahydrofolate we know is very, very important for purine synthesis and for pyrimidine synthesis. Now, part of the thing that gives you tetrahydrofolate is an enzyme that's called dihydrofolate reductase. Okay, so if you guys see tetrahydrofolic acid, that's your tetrahydrofolate. That's your TDF, right? It's called TDF, right? THF, tetrahydrofolate. One of the enzymes that's going to directly give you tetrahydrofolate is an enzyme called dihydrofolate reductase. Okay, you have these two drugs, which are methotrexate and trimethoprim, that are going to inhibit dihydrofolate reductase, and it's going to prevent the conversion of folate to tetrahydrofolate. And again, you need tetrahydrofolate for purine synthesis. So again, we talked about you need them for rapidly dividing cells. So what might you need this for? Well, it's used as treatment for cancer, so it's a chemotherapeutic drug, and it's also used as treatment for rheumatoid arthritis. Okay, so if you have gout, for example, or if you have like arthritis or cancer, this would be the perfect drug to use because it's going to inhibit tetrahydrofolate synthesis by inhibiting this enzyme dihydrofolate reductase, and this is going to deprive these rapidly dividing cells of like key components that they need in order to build these bases, these purine bases and these pyrimidine bases, and eventually make these nucleotides. Okay. One of the things that it can cause, because it's affecting dividing cells or rapidly dividing cells, it can cause macrocytic anemia. Because again, what else is very rapidly dividing? Blood cells, right? So macrocytic anemia, that's what it's going to cause. It's going to cause immunodeficiency because again, your immune cells are also fairly rapidly dividing, T and B cells, and they're going to cause baldness because you have your hair follicles, right? So they're going to attack these, or they're going to, deprive all these cells from key components of nucleic acid structure, and thus you're going to have all these adverse effects. I need you to remember macrocytic anemia. This is an important one to remember for methotrexate. Trimethoprim also has the same MOA, has the same mechanism of action, but it's not as high yield. Okay, so it also inhibits dihydrofolate reductase, but again, it's not as high yield. So again, if you see from this, if you look at this diagram, trimethoprim, and again, if you like just imagine the word methotrexate here, both of them inhibit this step, dihydrofolate reductase. Now you have sulfonamides. Sulfonamides, similarly to methotrexate, they also deprive cells of tetrahydrofolate. And this is a very important sentence, okay, because this exact sentence came in so many questions from last year, like practice questions and also the exam. But they inhibit a reaction that is not present in humans, and thus they are used as antibiotics. Okay? This specific drug, you're going to take it more in second year, in POD, inshallah. But for now, all you need to know is that bacteria, they have the specific reaction that's only present in bacteria. It's not present in humans. Okay? And this is the enzyme dihydropteroate synthase. Okay? Dihydropteroate synthase. Again, you don't need to remember the name because if you get asked about this drug, you're going to be like the answer is going to be they inhibit a reaction that is not present in humans. It won't give you the actual drug name or the actual enzyme name. Inshallah, like it shouldn't. Okay? Because you guys haven't like taken it yet in detail. So again, sulfonamides, they inhibit a step, they're used as antibiotics because they inhibit a step in tetrahydrofolate synthesis that's only present in bacteria. It's not present in humans. So they don't have like any adverse effects like methotrexate does, because methotrexate inhibits this step, dihydrofolate reductase, which is present in both, which is like it is present in humans. But sulfonamides, it attacks bacteria because the enzyme that it targets is not present in humans. It's only in bacteria. Okay? Does that make sense?
Yes.
Okay. Perfect. Now I mentioned, and this is why it's important to pay attention to these tiny little details, such as like feedback inhibition, stuff like that, because I mentioned deoxy ATP, DATP inhibiting ribonucleotide reductase. Do you guys remember that? I mentioned it back here, right? Inhibited by DATP. You guys see that? Ribonucleotide reductase inhibited by DATP. This is why it's important. Okay, now this is a bit of a what's it called? Like it's a bit of a thought process. You guys need to stay with me on this. Okay, so try to if you've been sort of zoned out for the last little bit, try to pay attention now because this might take a little bit of explanation. Okay, where were we? Okay, so we have this enzyme, as I mentioned, IMP can turn into AMP. Okay, but now let's say there's too much AMP in the body. We need to degrade AMP. I want to break down AMP. I want to get rid of this AMP in my body. I want to turn it into hypoxanthine and then xanthine, then uric acid, and then excrete it in the urine. I want to get rid of it entirely. What do? I'm going to take this adenosine and I'm going to turn it back into inosine so that inosine can go and get turned back into hypoxanthine and then xanthine. Do you guys remember that? So if I go back to this, I think it was in this slide. Yeah, sort of low quality, but it's still readable. It should be fine. So again, IMP turns into AMP. AMP can give you adenosine. Now, if you want to break down this adenosine, it's going to turn back into inosine so that it can be excreted as uric acid. Okay? Because you can't immediately go adenosine, uric acid. You can't do that. You have to go back to inosine and have that turn into the uric acid eventually. Okay? But what if this enzyme that's going to take adenosine and turn it back into inosine, what if we're missing this enzyme? Okay? This enzyme is called adenosine deaminase, ADA. Okay? Now, stay with me on this. We're missing this enzyme. This enzyme is gone. What do we have now? We have too much adenosine. We have way too much adenosine in the body going on. We have way too much adenosine in the body. Adenosine is then going to have no choice but to try to turn back into like a ribonucleotide. So it's going to eventually, through a number of steps, turn into deoxy ATP. Okay? Deoxy ATP. And what does too much deoxy ATP inhibit? Ribonucleotide reductase. And what did I say about these about this whole lecture? What did I say about these drugs and about these scenarios, these adverse effects of all these drugs? they're going to cause some immunodeficiency because you're going to be attacking, or you're, sorry, not attacking, you're going to be affecting these rapidly dividing cells, one of them being immune cells. So if you have too much ATP, or sorry, DATP, deoxyadenosine triphosphate, all of that DATP is going to go back and it's going to inhibit ribonucleotide reductase. And thus, again, you're doing the same thing where you're not allowing, you're depleting these rapidly dividing cells from the major components needed for nucleic acid structure or DNA building, DNA replication. This is an important, what we call this is part of something that's called SCID. SCID stands for severe combined immunodeficiency. Okay, it causes a type of SCID because these high levels of DATP are going to inhibit ribonucleotide reductase, and thus you're going to basically be depleting immune cells from like main things that they need in DNA synthesis. Okay, so extremely large buildups of DATP in blood cells have been observed. It's an inhibitor of ribonucleotide reductase and therefore of DNA synthesis. Okay, so the children, the people that have adenosine deaminase or ADA deficiency, because they have such high levels of DATP, they're going to have severe immunodeficiency. That means even like a common cold can kill them because they have such weak immunity because of a lack of immune cells being able to rapidly proliferate, rapidly divide. Does that make sense? So if you think, if you remember ADA or adenosine deaminase, SCID, that's enough. ADA deficiency has to do with SCID and like immunodeficiency in general. Does this part make sense? I'm sorry, I know I'm asking this question a lot. Does this make sense? This makes sense, but it does take a little bit of explanation to sort of get it, because it's like multiple steps that you have to walk through in order to get to your outcome. Do you guys see why an ADA deficiency would cause, first of all, accumulation of adenosine, and therefore because it's an accumulation of adenosine, you're going to have too many or like high levels of DATP. This DATP is going to go back and inhibit ribonucleotide reductase, which again turns ribonucleotide to deoxyribonucleotides. And deoxyribonucleotides, we need them for DNA synthesis. So if you have too much DATP, and too much inhibition of this enzyme, you have no more deoxyribonucleotides, and thus you're depriving these cells of things they need in order to divide. And that's why you would have immunodeficiency. And lymphocytopenia. This is actually an important point. Lymphocytopenia. Because these cells can't divide, you would have T and B cell depletion. That's part of the immunodeficiency. Actually, that's the whole thing. Does that make sense?
Yes.
Okay. All right. We don't have much more, inshallah. So this is, I'm sorry if this picture is a bit if it's a bit graphic. I just had to include it because I need you guys to understand the most important symptom in this condition. So if we're going through the thing again, we've talked about purine synthesis and we've talked about the de novo synthesis, and we talked about specific cases, specific pharmacology and clinical situations. So we have mycophenolic acid that inhibits IMP dehydrogenase. It's used to prevent graft rejection. Then we have methotrexate and trimethoprim and sulfonamides, which all of them collectively inhibit synthesis of tetrahydrofolate. But the difference is sulfonamides are antimicrobials. They are antibiotics. And methotrexate is a chemotherapeutic drug and also used for RA or rheumatoid arthritis. And it may cause macrocytic anemia too, because as an adverse effect. And then we talked about adenosine deaminase deficiency and how that has to do with SCID. So that basically covers everything from the de novo synthesis. Now there's the salvage pathways. If you guys remember the salvage pathways, I told you to remember just one enzyme, one specific enzyme. That's the HGPRT, hypoxanthine guanine phosphorybosyltransferase transferase. So again, to the salvage pathway, what you're doing is you're taking a preformed base and you're attaching it onto a ribose sugar. And that way you already have there you go, like that's your nucleotide. So a deficiency in this enzyme would cause something called Lesh-Nyhan syndrome. Now, Lesh-Nyhan syndrome, it's basically one of, it's one of the, it's the most serious condition basically in the sector, or it's the most like graphic, I would say, because the main thing, and I need you guys, like, if there's one thing that you need to remember about this syndrome, about this disease, just remember self-mutilation. Okay, so you see, so like this is an example. So patients that have HGPRT deficiency will self-mutilate. So either they're going to bite off their fingers, like they will straight off bite off their fingers clean, or they're going to bite their lips and like rip their lips off. So this is what you see in this case. So if you guys see this person's gums and their lips and everything like that, it's a form of self-mutilation, and they have mental retardation and, of course, hyperuricemia, which again is increased level of uric acid in the body. Okay, so the main thing you need to remember about HGPRT is self-mutilation. Now, why is that the cause? Like, why does HGPRT deficiency cause self-mutilation? We don't know. Nobody knows, but it does. So you just you need to remember it. If they ever get a question and they're telling you, a child he has a slow mental development, he has mental retardation, and he bites off his fingers or his lips, immediately you're going to think Lesh-Nyhan, or you would think deficiency of HGPRT, hyperxanthine guanine phosphoribosyltransferase transferase. Okay, does that make sense? The hyperuricemia, it's because basically if you don't have HGPRT, you have too much hypoxanthine and guanine. What's hypoxanthine going to turn into? And guanine is going to immediately turn into xanthine, and then uric acid, and then you would have too much uric acid, and then you would have hyperuricemia. Okay, this is not like a adenosine deaminase, because if you guys remember, adenosine needs to turn into inosine in order to be excreted. So if you have too much adenosine, it's not going to be excreted. It's not going to turn into uric acid because it's going to not be able to reach that stage. But with hypoxanthine and guanine, this is a point that I actually forgot to mention. But guanine, it's not that much of an important concept to remember. Guanine can actually, unlike adenosine, guanine can immediately turn into xanthine. Okay, but adenosine has to turn back into inosine first. So in this case, if you want to degrade it, if you have too high levels of guanine or hypoxanthine, it's going to immediately be degraded or break down to uric acid. And that's where the hyperuricemia is going to come from. That's going to be your Lesh-Nyhan syndrome. Okay, HGPRT deficiency, Lesh-Nyhan, self-mutilation. Like if I could sum up this slide in 3 words, I would say HGPRT, Lesh-Nyhan, self-mutilation. That's what I would say. And that's enough. Okay. And again, you have ribonucleotide reductase itself. It's inhibited. So as I mentioned, ribonucleotide reductase is inhibited by high levels of deoxy ATP that has to do with SCID, if you guys remember. But it's also inhibited by a drug called hydroxyurea. Okay? If it's inhibited by a drug called hydroxyurea, it's used as a cancer treatment because it's more of the same thing. So far, by the way, we've taken a few, I'm pretty sure we've taken a few drugs that are chemotherapeutic. So far, I think, and let me know if I'm forgetting something. It's methotrexate so far and hydroxyurea. Am I forgetting anything? Hydroxyurea. No. Sulfonamides. No. Okay. No. Okay. So far, methotrexate and hydroxyurea, both of them are used as chemotherapeutics, as anti-cancer drugs. All right. And again, it's used as treatment for sickle cell anemia. So if you have somebody with sickle cell anemia, you give them hydroxyurea in order to inhibit the ribonucleotide reductase step. All right. The explanation for this, you guys don't need to know it, but if you'd like to know, it's because, as you guys know, in sickle cell disease, there's actually something genomically wrong, like with the genes itself. There's a what is it? Was it a translation or a? I'm not sure. There's a problem in one of the codons for sickle cell anemia. I forgot what the exact problem was, but in that case, then those cells, those blood cells, when they divide, they would be sickle shaped, and that would cause basically like blood clots, and they would mess up the blood vessels and all that. So you basically want to put an end to that. You want to stop blood vessels from proliferating, and that's why you would use them as treatment. That's why you would use hydroxyurea. That's why it's treatment for sickle cell anemia. Okay, so again, hydroxyurea inhibits ribonucleotide reductase. Okay, and in this way, we should be okay. Now we get to gout. Actually, perfect. All right, this is fairly simple, the gout thing. Okay, because there's basically gout is basically the underlying issue of hyperuricemia is gout. Okay, that's the big clinical case in both of these lectures. Now, gout, as I mentioned, it's caused by under excretion of uric acid or overproduction of uric acid. Either way, you're going to have hyperuricemia. Okay, if you're excreting too little uric acid, you're going to have too much uric acid in the blood. And if you're producing too much uric acid, then you're going to have too much uric acid in the blood. Either way, it's going to be the same thing. Okay, seafood and red meats are high in purine content, so they can exacerbate effects. Okay, so if you see a question, and by the way, we got this as an SAQ last year in our MOL 2 final. The SAQ was a guy, I think, who was eating seafood, and then he had a bunch of problems and like arthritis and stuff like that. We had to describe his entire case and give him the treatment and everything like that. So seafood, think seafood purine content. So if somebody has gout and they eat seafood, it can make that gout worse. That's not to say that it can cause gout, because again, this is dietary purine, so it's not that it's not that important as compared to the body's endogenous purine production, but it will exacerbate the effects. Acute attacks, because I mentioned actually, I'm not sure if I mentioned this, but gout is a inflammatory attack. Okay, so at first gout is inflammatory, and then later on, when it's chronic, that's when it can turn into gouty arthritis. So that's why acute attacks of gout are treated with anti-inflammatory meetings. I think this is supposed to say something else. Let me change that really quick, actually, because I don't want to. Anti-inflammatory agents, right? And chronic cases are treated with allopurinol, which is an inhibitor of xanthine oxidase. So I mentioned, guys, that you have GMP and guanosine and like guanine, and then guanine can turn into xanthine. Do you guys remember that whole thing where I told you that hypoxanthine and guanine can both turn into xanthine immediately, but adenosine has to turn into inosine first, right? Now, to give you xanthine and uric acid, you have this enzyme called xanthine oxidase. Okay, allopurinol is an inhibitor of xanthine oxidase. So one way to treat gout would be to administrate allopurinol, because it's going to inhibit the enzyme that's going to give you the uric acid, and thus you're basically lowering levels of uric acid in the blood. Okay, the other drug, and I didn't write it down because I don't think it's high yield, because Dr. Hannah didn't mention it in our she didn't mention it explicitly in our lecture last year, and there were no questions about it. But you just have to know it's probenecid. Like, you don't have to remember the second name, sulfentrazone. All you have to know is probenecid, and that's going to cause excretion of uric acid. Okay. And then the last thing is the tumor lysis syndrome, and I didn't make this. I could have made this a slide on its own, but I didn't, because I didn't think it was too high yield. We didn't get any questions about it either, but it's a fairly simple concept. Basically, when you're killing cancer cells, so in chemotherapy, when you're lysing, basically what you're doing is lysing tumors. Because these tumors are dying, they're degrading their ribonucleotides and they're degrading their purines, and eventually you're going to have a buildup of uric acid in the blood. So one of the side effects of any chemotherapeutic drug or any like tumor lysing drug or any sort of treatment is gout, because it can increase levels of uric acid in the blood, since these cells are giving off, like, they're degrading their purine way too fast. Does that make sense to everyone so far? We've talked about a bunch. I understand that. I know it's a bit much, but inshallah, there's a what's it called? There's a table at the end of Dr. Hannah's slides in Nucleotide Metabolism II. There's a table at the very end, the very last slide, and it gives you every single drug and what it's used for and which enzyme it acts on. Very helpful table. I really, really recommend that you guys look through that table very, very quickly when you're studying this section in the future. Okay? All right. Now, von Gerke syndrome. Okay, this is another one of those things where you guys have to stay with me for a little bit. Do you guys remember the whole thing with ribose 5-phosphate and the HMP shunt? Do you guys remember that?
Yes.
Okay. So if you guys remember from glycolysis, glucose 6-phosphates, the molecule glucose 6-phosphate, that's where that molecule is going to branch off and give the HMP shunt. So the first thing that's going to basically drive the HMP shunt, it's glucose 6-phosphate. Okay, but again, glucose 6-phosphate is one of those molecules that can go into different. It can go in multiple directions. It can go in multiple different directions. It can either go into glycolysis, or it can go into the HMP shunt. Now, if you have a deficiency in the enzyme that takes it in the direction of glycolysis, where is it going to go? Where's glucose 6-phosphate going to be driven to?
The HMP shunt.
The HMP shunt. So, and what's the HMP shunt going to give you? Too much
Ribose 5-phosphate.
ribose 5-phosphate. Stay with me. Stay with me. What does ribose 5-phosphate give you too much of?
Synthesis of IMP.
Eventually, yeah, but like
Yeah, eventually.
PRPP, and then the de novo synthesis, and then PRPP, and eventually, so on and so forth, and then you have IMP, AMP, GMP, and then degradation, and then uric acid, hyperuricemia, right?
Yes.
So basically, you're cutting off something at the very beginning, and then it's going to lead all the way down to hyperuricemia because you're cutting off this enzyme that's going to basically lower levels of glucose 6-phosphate in the body. The enzyme, I'm not sure if I mentioned it, it's glucose 6-phosphatase.
Yes.
Okay, so the molecule is glucose 6-phosphate. You have a deficiency in glucose 6-phosphatase, and thus you're going to have glucose 6-phosphate driven into the HMP shunt, overproduction of ribose 5-phosphate, overproduction of PRPP, overproduction of purine nucleotides, and because you have overproduction of them, what's your body going to do? Get rid of them. You get rid of them, you have too much degradation, it's going to cause hyperuricemia and then gout. This is called von Gerke syndrome. Does that make sense?
Yes. So in a nutshell, we can say that he would also have hypoglycemia in addition to hyperuricemia.
That's true. That's true. But I want you guys to focus specifically on this picture, the diagram that I added. It was a full picture. Like there's von Gerke akid. It's not that simple. It's not as simple as just hyperuricemia because this is a very important enzyme that you're cutting off. You will have hypoglycemia, but I do want you guys to just focus on hyperuricemia for now, just because it makes things a lot easier. So, but yes, it will give you hypoglycemia. All right. So yeah, hyperuricemia, von Gerke syndrome, glucose 6-phosphatase deficiency. All right. Now, wow, mashallah. All right, so we're done. We're pretty much done the de novo synthesis and every clinical condition with it and every drug with it, and the salvage pathway of the purine synthesis and every drug with it and every single clinical situation with it. Now let's get into the pyrimidine synthesis and then we'll be done. And then we'll just do some questions. Okay. Deficiency. Again, I mentioned that you guys have this thing called UMP synthetase or synthase, whatever you guys want to say. Okay, it's made up of these two domains of one enzyme, these last two. Okay? Okay. Deficiency of this enzyme, because, sorry, I want to mention one last thing. So you guys see here you have CPS2. Okay, eventually all these steps are going to take you to something called orotate, which is orotic acid. Okay? If you have a deficiency in these two drugs, 1 and 2, what's going to happen to this orotate? It's going to, levels of it will increase, and you will have overexcretion of it in the urine because your body's trying to get rid of it too fast. So you will have something called orotic aciduria. This is a deficiency of UMP synthase. What is it also going to give you? And Yasser mentioned it at the very beginning of this bout, megaloblastic anemia. Okay, this deficiency is very easy. There's really not much to remember. All you have to know is orotic aciduria with UMP synthase deficiency, and it will cause megaloblastic anemia. And it's for the same reason that we've talked about for all the other things. It's because rapidly dividing cells, depleting depleting, components of ribonucleotides, or like DNA synthesis, and that's why it will cause megaloblastic anemia. Okay. Treated with uridine. Why do you guys think it's treated with uridine? Because if we're giving uridine, then, and by the way, the final, as I mentioned, the final product of pyrimidine synthesis is uridine monophosphate. Okay, but we need to get through these two steps, the UMP synthase steps. But if we have a deficiency in this enzyme, and we just treat that person with uridine, then we basically bypass the need for this step. We don't need these two steps to happen anymore because we're already giving exogenous uridine that can immediately be converted to uridine monophosphate. So we take away the need for our bodies to go through these two basically steps. Does that make sense? So UMP synthase will cause orotic aciduria and megaloblastic anemia, and it's treated with uridine. Okay. Do you guys remember that whole thing that I mentioned about tetrahydrofolates, that it's important in both purine synthesis and pyrimidine? And I mentioned for one of these slides back here, let's go back just a little bit. Yeah. Where was it? Not here. Here. Remember I mentioned here that we have this enzyme called thymidylate synthetase, which will take the DUMP, the deoxyuridine monophosphate, and turn it into deoxythymidine monophosphate. And do you guys remember how I mentioned that we need tetrahydrofolate for this step? Okay, this is where it comes into play. So, oh, there's a lot. Sorry. Okay. In biosynthesis of pyrimidines, tetrahydrofolate also plays an important role. Methylene tetrahydrofolate donates a methyl group, okay? Donates a methyl group, so methylene tetrahydrofolate, it donates this methyl group to deoxyuridine monophosphate in order to form deoxythymidine monophosphate. This is the same thing that I was telling you about. This is the same enzyme, thymidylate synthase. Okay, so what this enzyme is doing, thymidylate synthase, is it's taking a methyl group from tetrahydrofolate and putting it onto a deoxyuridine monophosphate molecule to turn it into DTMP, to deoxythymidine monophosphate molecule. Now, 5-fluorouracil is an anti-cancer drug that inhibits thymidylate synthase. Okay? Thymidylate synthase is inhibited by the drug 5-fluorouracil, which is an anti-cancer drug. It's a chemotherapeutic drug. All right? So now we've taken 3 anti-cancer drugs, right? Can somebody remind me what those 3 chemotherapeutic drugs were? So preferably somebody other than Yasser, just because I know there's other people listening. If you guys want to type it out, that's fine too. And if nobody answers within like a minute, then Yasser can answer. I think that's fine too. If anyone would like to. No? Okay. No worries, it's fine. So the 3 drugs so far were methotrexate, inhibiting dihydrofolate reductase.
Someone answered with methotrexate and hydroxyurea.
Perfect. Exactly what I'm looking for. And now 5-fluorouracil. It's perfect. Thank you so much to whoever answered. Hydroxyurea, inhibiting ribonucleotide reductase. Methotrexate, inhibiting dihydrofolate reductase. And 5-fluorouracil, inhibiting thymidylate synthase. All right? And that's it. We're done. We're done those 2 lectures. Now let's just run through some questions. Okay. You are examining a 7-year-old male child who exhibits delayed motor development, over-exaggerated reflexes, and spasticity. In addition, the boy has a tendency to chew his lips, right? You guys with me? Chew his lips and fingers, often causing tissue damage and bleeding, and his painful, swollen, and inflamed joints. I guess they mentioned the name. The most likely diagnosis in this case is Lesch-Nyhan syndrome. Analysis of blood from this patient would be expected to find elevated levels of which of the following compounds related to the observed findings? Citrulline. Hypoxanthine. Why would you answer hypoxanthine? Why do you think so?
Because there would be a problem in the xanthine oxidase enzyme, which can convert hypoxanthine to xanthine and then xanthine to uric acid.
Okay. Not exactly, actually. If you remember, Lesch-Nyhan syndrome was not a problem. Was not a sorry. One second. I'm just going to charge my iPad.
Yeah, the
Yeah,
HGPRT. So hypoxanthine would be elevated because
true.
it would be a problem in salvage pathway.
It's true. It's true. It's true. It would like basically this. I'm glad I put this question in because it is a bit of a trick question. The enzyme is hypoxanthine guanine phosphorybosol transferase. Okay, but what does hypoxanthine turn to when there's too much? When there's elevated levels of of hypoxanthine, what will it turn into? Xanthine and then uric acid. And what was the question? To find elevated levels of which of the following compounds related to the observed findings. So what are the observed findings? Again, swollen and
Lesch-Nyhan
inflamed joints.
syndrome.
Yeah, but what are the observed findings in this patient? One of them, two of them actually, swollen and inflamed joints. What does that tell you? Gout.
Gout.
Gout. And what is gout caused by?
Hyperuricemia.
So the answer would be uric acid.
Uric acid.
So yes, you are right. Like Lesch-Nyhan syndrome is a deficiency in HGPRT, and HGPRT basically will take hypoxanthine and will turn it into IMP. That's very true. But then since you have an accumulation of hypoxanthine, it will be degraded further to give you xanthine and then uric acid, and that uric acid is what's going to go and cause all of these problems. So if I go back to this slide, which is why I stressed. Oh wait, I should not have gone that far. Where is it? Yeah. One of the things, look, I wrote three things. I wrote hyperuricemia, mental retardation, and self-mutilation. Hyperuricemia is the thing that's causing the swollen and inflamed joints. That's what's causing it. So what are you going to find elevated in the blood that's related to the observed findings? Uric acid and not hypoxanthine. Because hypoxanthine, while it might accumulate, while levels of it might be high, that's true, it's not related to the observed findings. But uric acid is. Does that make sense?
Yeah.
Okay. Perfect. Did anyone else answer, by the way, before I was able to show the answer?
Nope, I don't think anyone else.
Okay. Guys, if you know the answer, try to participate. So if you know it, if you don't, that's fine too. Okay. 5-fluorouracil is utilized as a chemotherapeutic agent because of its ability to interfere with the function of which of the following enzymes?
Do you want someone other than Yasser? Well,
No. Go ahead, yes.
yes, someone answered D.
D?
No, E. Someone
E.
answered D.
Okay, E. Perfect. The answer is E.
Let's see.
Okay, perfect. Fairly straightforward question. Okay, if you guys have any problems, I'm not going to explain this question because it's a bit of a recall question. But if you guys have a problem with it, let me know. Okay. Severe combined immunodeficiency disease (SCID) is characterized by a complete lack of cell-mediated and humoral immunity. This disorder results from a deficiency in which of the following enzymes? Again, a
Someone
pretty
answered A.
perfect. What do you think, Yasser?
Yeah, it is A. ADA deficiency.
Perfect. Can you tell me, can somebody, even Yasser if you want, can somebody tell me why? What exactly
So
is
this
happening?
would be inhibited by the too much DATP, which can also cause any decreased division or production or whatever of T cells and B cells.
Exactly. Perfect. And that enzyme would be ribonucleotide reductase. That's the enzyme that's basically that DATP is inhibiting. Perfect.
Yes.
Thank you so much. Okay. A penicillin allergic child was given a sulfonamide for otitis media. Otitis media is inflammation of the middle ear, by the way. Human cells are resistant to sulfonamides due to which of the following? A, sulfonamides are specific for prokaryotic DNA polymerases. B, sulfonamides are specific for prokaryotic RNA polymerases. C, sulfonamides inhibit a metabolic pathway not present in eukaryotic cells. D, sulfonamides inhibit bacterial ribonucleotide reductase, but not eukaryotic ribonucleotide reductase. E, sulfonamides inhibit prokaryotic mismatch repair, but not eukaryotic mismatch repair.
Someone answered C.
C. Perfect. Mashallah alaikum. Perfect. It's C. Okay. So again, it wouldn't be A or D, or sorry, A or B, because we never mentioned DNA polymerases, right? It has nothing to do with DNA polymerases. DNA polymerase is more of the actual replication of it. Here, this has to do with the whole like tetrahydrofolate pathway thing. Okay. Again, it's not ribonucleotide reductase. The enzyme actually would be the hydropteroate reductase for sulfonamides. That doesn't really matter. Again, it's C. And I think this should be the last question. Your 60-year-old female patient has psoriasis and has been treated with methotrexate for several years. She has no other medical problems, and her preventive screenings, including fecal occult blood tests and colonoscopy, have all been normal. She has developed an anemia. Which of the following would you expect to find when working up her anemia? Macrocytic, microcytic, thalassemia, spherocytes, low B12.
It would be macrocytic.
Macrocytic. Perfect. And it's that easy. Okay. Thank you guys so much for paying attention and for sticking with me. And please scan this code and judge me however you want to judge me on the form. Does anyone have any questions?
Everything is clear.
Everything's clear. I'm so glad. Thank you all so much. And thank you, Mariam.
But by the way, Rawad, your
Yes.
name is not found in the